Creatives fight back. Artists are rebelling against AI-driven imitation. DeviantArt, an online community where artists display and sell their work and marketplace for digital art, launched DreamUp, a text-to-image generator that aims to help artists thwart attempts to imitate their styles or works. DreamUp is a vanilla implementation of the open-source Stable Diffusion text-to-image generator. Artists can fill out a form that adds their name, aliases, and named creations to a list of blocked prompt phrases. DreamUp labels all output images as AI-generated. Users who upload the system's output to DeviantArt are required to credit artists whose work influenced it. DeviantArt users can report images that they believe imitate an artist's style. In unclear cases, DeviantArt will ask the artist in question to judge. DeviantArt offers 5 free prompts a month. Members, who pay up to $14.95 for a monthly subscription, get 300 prompts a month or pay up to 20 cents per prompt. Stable Diffusion was trained on images scraped from the web, including works from DeviantArt. Upon its release, some artists objected to the model's ability to replicate their style via prompts like, "in the style of ________". DeviantArt opened fresh wounds upon releasing DreamUp by offering members the opportunity to add HTML and HTTP tags that specify that work is not to be included in future training datasets, but only if they opted in. Members objected to having to opt in to mark their works as off-limits to AI developers. DeviantArt responded by adding the tags to all uploaded images by default. It's not clear what consequences would follow if an AI developer were to train a learning algorithm on such tagged images. Built to scale, a new computing cluster delivers more bang per chip. Cerebras, one of several startups vying to supply the market for specialized AI chips, unveiled Andromeda, a supercomputer based on its processors. Unlike conventional clusters, which incur data bottlenecks as processors are added, the system's processing speed rises linearly with additional processes. Cerebras, one of several startups vying to supply the market for specialized AI chips, unveiled Andromeda, a supercomputer based on its processors. Unlike conventional clusters, which incur data bottlenecks as processors are added, the system's processing speed rises linearly with additional processes. Andromeda comprises 16 Cerebras CS2 wafer-scale engine chips. Each chip holds 850,000 processing cores, more than 100 times the number found on an NVIDIA A100, on a silicon disk that measures 21.5 cm across. The cluster can execute more than 1 exascale floating-point operation per second, which is comparable to the world's fastest supercomputer, Oak Ridge National Laboratory's Frontier. A memory extension called Memory X stores model weights off system and streams them to the processors as needed. Up to 16 users can access Andromeda simultaneously, and they can specify how many of the system's 16 processes they wish to use. Several companies are using Andromeda for research, including rival chip designer AMD and natural language processing startup Jasper AI. Champion model is no-go. A new algorithm defeated a championship-winning Go model using moves that even a middling human player could counter. Researchers at MIT, UC Berkeley, and the Fund for Alignment Research trained a model to defeat Kata Go, an open-source Go playing system that has beaten top human players. The author's system tricks Kata Go into deciding prematurely that it has won, causing it to end a game when the author's model is in a winning position. The author's system tricks Kata Go into deciding prematurely that the authors trained a convolutional neural network to play Go using a modified version of a reinforcement learning method commonly used to train game-playing models. In the usual approach, the model plays itself and learns from all moves. In the author's version, the model played against a fixed Kata Go model and learned only from its own moves, learning to exploit holes in Kata Go's strategy rather than becoming a conventionally savvy player. The author's model forecasted its next moves using its own model, and it forecasted Katago's likely responses to those moves using Katago's model. It combined the forecasts to determine its next action. Katago can be configured to perform similar forecasting, but the authors didn't use this capability while training their model. During training, once the model had won 50% of games, the authors increased the difficulty by pitting it against a version of Katago that had been trained longer. The model's winning strategy involved taking control of a corner of the board and adding a few easy-to-capture pieces outside that area. When trees outdo neural networks while neural networks perform well on image, text, and audio datasets, they fall behind decision trees and their variations for tabular datasets. New research looked into why. Leo Grinstein, Edouard Oyalen, and Gail Varaquaux at Inria Sackley Center and Sorbonne University trained a variety of neural networks and tree models on tabular datasets. Performance on the tabular data learning benchmark revealed dataset characteristics that favor each class of models. The authors compiled datasets, trained a variety of models, using a variety of hyperparameters, and evaluated their performance. Then they applied transformations to the data, retrained the models, and tested them again to see how the transformations affected model performance. The authors collected 45 tabular datasets useful for both classification problems like predicting increase, decrease in electricity prices and regression problems such as estimating housing prices. Each dataset comprised more than 3,000 real-world examples and resisted simple modeling, that is, logistic or linear regression models trained on them performed 5% worse than a ResNet or gradient boosting trees. The authors trained tree-based models, random forests, gradient boosting machines, XGBoost, and various ensembles, and deep learning-based models, vanilla neural network, ResNet, and 2 transformer-based models. They trained each model 400 times, searching randomly through a predefined hyperparameter space. They evaluated classification performance according to test set accuracy and regression models according to R2, which measures how well a model estimates the ground truth data. In one transformation of the data, they used a random forest model to rank the importance of a dataset's features and trained models on various proportions of informative versus uninformative features. In another, they smoothed labels like 0 or 1 into labels like 0.2 or 0.8. Averaged across all tasks, the best tree models performed 20% to 30% better than the best deep learning models. ResNets fell even farther behind trees and transformers as the number of uninformative features rose. In another experiment, training on smoothed labels degraded the performance of trees more than that of neural networks, which suggests that tree-based methods are better at learning irregular mapping of training data to labels.